everyone. There's something that I want to discuss with you, okay? Because last time some of you asked me if I can solve the quiz, and it was not with me. So the professor sent me the quiz, okay? And I also asked him to give me the second quiz, okay? So, yeah. And I feel somehow partially guilty for that because the question that I went through it fast, okay? If you remember in the second recording, I guess, or the first recording, the one with the entropy and the exergy. I solved the same question. It is example 813 in the book, okay? Example 813. Okay, but I went through it quickly. I didn't solve it step by step because the session was somehow long. So I don't know. I'm gonna solve the question, okay? And as well the tutorial, the second quiz question, okay? And if we have time, maybe I can start with chapter 10 questions also, solve them. I have 2 questions. If no, then yeah, I'm just gonna stick to solving the quiz this time. And also I want to make a poll or something to make sessions for the midterm review. I don't know, maybe 1 session or 2 sessions. I don't guess 1 session will be enough, so maybe 2 sessions. Yeah, because I don't know, I feel like maybe you don't have time in the tutorial session to attend it in person, but like this will not make it very active. I want to make sure that all of you can solve problems. The theory things are, I guess it's on you. It's not gonna take that much time or effort, but solving needs somehow practicing, okay, and realizing where are your mistakes. If you solve actually the homework problems alone, okay, then I guess it will be fine. But I don't know if all of you solve the homework questions alone or not. So yeah, okay. Okay, I'm gonna start now by solving the questions. So the first part, which was the theory part, we have a furnace, okay, that transfers heat at 1100 Kelvin, okay, and at a steady rate of 3000 kilowatts. Using a heat engine concept, it can be calculated that the furnace has an exergy rate of 2187 kilowatts and an available energy of 813 kilowatts. So we can get this number actually, okay, and this number also. How can we get them? Remember from chapter 6 in thermodynamics, if we want to calculate the thermal efficiency of the reversible cycle, okay, or let's call it the Carnot cycle, because that's the maximum efficiency that we can get, okay, for a reverse cycle or for Carnot cycle. It's going to be equal to 1 minus the temperature of the sink, okay, TL, over the temperature of the source, yeah? So it is 1 minus 1, okay, we assume that the sink is in the environment, which is 25 degrees Celsius or somewhere around that point, plus 273, don't forget to convert the units, over 1100. So the Carnot efficiency is going to be, okay, let me get my calculator. It's going to be 1 minus 25 plus 273 over 1100. So it is around 37%, okay? Oh, sorry, 73%. Yeah, and now when we want to find the work output of the cycle, so work dot or power dot net is going to be equal to the heat, okay, QH, because this is a heat engine, multiplied by the efficiency, which is going to give us, in the end, 3000, okay, multiplied by 73%, okay. It is 2190, okay, kilowatts. So which is fairly close. Maybe they choose the environment temperature of 23 or something like that, okay. So this is the answer. Now, this is the energy or the exergy that is available for us, okay? Because the exergy transfer by heat, if you remember, the exergy transfer by heat, X by heat, is the same thing. It is Q multiplied by 1 minus T, okay, of the environment, which we call T naught, over the temperature of the boundary, yeah? The temperature of the boundary that you have there, which was in our case for the source, it is TH. But how can we eliminate the energy that is lost, okay, due to this transfer, okay, because now the exergy is the maximum work that we can get, yeah, it's the maximum work that we can get from a process. And now this furnace is able to give us this amount of heat rate, or okay, let's make it in rates. It's able of giving me 3000, okay, kilowatts heat rate. So not all of it is going to be converted into work, obviously, because it's not part of the mechanical energy. Remember that the mechanical energy is the only form of energy that can be fully transferred to work, okay, or to produce power without any loss. But the heat transfer process obviously doesn't have that. So we had some losses, as he told you in the question, okay, of 8 and 13, okay, 813 kilowatts. So he wants you to discuss the unavailable energy and the possibilities of eliminating this unavailable energy. Of course, realistically, it cannot be eliminated. But what can we do in this process, okay? In this process, or in this case, exactly, we can raise the temperature, okay, of the source. So when we raise the temperature of the source, we increase the efficiency, okay? So the efficiency will be increased, and then therefore we approach 100% efficiency, which is not actually realistic, but we can do that. Or maybe if we can make use of mechanical energy in our system. So how can we do that if we make use of mechanical energy? Let me show you a problem. I think most of you know, maybe those also who took fluid mechanics, okay? So I have here a water storage system, okay, or a water reservoir, okay, water. And I have here a pipe, okay, and here I have the river, okay, basically just let's call it river, okay, river. And I have here a fan that I want to drive, or a turbine that will extract this work, or this flow of water, okay? When it passes from here due to the gravity, then it's going to give me work in this fan, yeah? So this is work dot out. How much is this work dot out? It is equal to this work dot out equal to m dot g z, okay? m dot gz. This is the work dot out that I'm going to get, which is of course the same as the exergy, yeah? So there is no losses, fully converted to work, exactly. The amount of potential energy that was transferred from this storage reservoir to the river due to gravity is fully converted here to work. Yes, you remember this problem? I think you solved like it in chapter 2 in thermodynamics and also in fluid mechanics. So yeah, if I give you the elevation here, okay, you can control it, of course, how much height you want your reservoir to be, okay, and you know now the flow rate of water, and the G is the acceleration due to the gravity, then you can know the exergy rate that you will get from this reservoir. Yeah, so that's the possibilities of eliminating the unavailable energy. Either you need to use mechanical forms of energy, okay, or if you can't do that, you can rise the temperature of the source to a certain level, okay, maybe till the material limitations that you have there or somehow, but of course you're not going to reach 100% efficiency. Yeah, so always remember it as this chart. Okay, I'm going to draw it to you. So you have the total energy. Okay, that's the total energy. Okay, and when we convert this total energy, okay, or if we want to divide it, then we have portion, okay, which is the exergy, and we have here the unavailable energy, and then again, if you have exergy destruction during the process, okay, then again you're gonna take some from this exergy, okay, so the unavailable energy, and maybe I have here some exergy destruction, okay, so I call it X destroyed, okay, and this is the useful exergy, or the rest of the exergy that I have for my system. So always you try to minimize the exergy destroyed as much as possible, okay, and if you use mechanical forms of energy, then you're not gonna have any exergy destroyed, okay. Yes, so that's the answer for the theory question. Now the second question, which is the similar to the example, but very much easier. Just that you need to find two things, okay? What are the two things that you need to find? You need to find the exergy of iron at the initial state, and you need to find the exergy change of water from the initial to the final states. So what is the exergy of the iron at the initial state? Well, this at the beginning depends on the system that you define. So this is the water tank, okay, and it's a closed system. And then now here's your iron that was dropped, and here's the water. So it is much preferable to deal with the iron and the water as a combined system, okay, inside this water tank. Some of you didn't do that, but it will make the problem longer for you. But if you deal with it in this way, if you know your system and you choose the best system possible to represent this problem, then you are going to solve it correctly. Sometimes if you choose the system wrongly or in a bad way, then you are going to solve it totally wrong, okay? So I prefer to use it as to deal with it as a combined system, yeah? So you don't have any exergy transferred by heat, which is the 1 minus T over T multiplied by Q. You don't have any of that because it is a closed system. If we have heat interaction, then it's going to be between the iron and the water inside the system, okay? It's not outside of the system. So we don't have to include the heat part, okay? So what's the exergy of the iron in the initial state? That's 1, so X, okay? Okay, I'm going to use the Exergy balance equation. So delta X of the system is equal to what? Okay, it's not better to use the Exergy balance here because we don't have process, we just have 1 point. So we say that we have delta phi, yeah? The Exergy change of the system. Yeah, but between which points, sorry, not the Exergy change, the Exergy at the initial state. So we make the change between state 1 and the environment state. Okay, remember, Exergy is already a combined property between the system and the environment. So basically, when he tells you the Exergy change, the Exergy at the initial state, this means the Exergy change between point 1 and the environment point, okay? So what is it for a closed system? Of course, it's a closed system, not an open system. So it is U minus U naught plus P naught V minus V naught plus or minus T naught multiplied by S minus S naught, okay? And then plus, of course, the mechanical energy forms, which are the kinetic and the potential energies, which are going to be zeros in this case, okay? Because we don't have either a nozzle nor a diffuser. And those are the only two devices where we have somehow considerable kinetic energy. Okay, maybe in other devices, maybe you have some elevation, high elevation, maybe in a turbine. So we need also to include the potential energy. But in this case, it's just this small tank. So we don't have neither of these. So yeah, and what also we don't have this term. It is 0. Why? Because these two materials that constitute our system are incompressible materials. Yes, the water is incompressible, and the iron is also incompressible. This is a solid and a liquid. They are not gases, so they don't have change in volume. So this is also 0. Okay, and also he tells you here an important information. Assume that the water that vaporizes during this process condenses back in the tank. So whatever whatever water that vaporizes, okay, which is going, of course, to change the volume. You may tell me, yeah, there is some water vapor that's going to form, and this will change the volume of water. Yeah, but it will condense back. That's the assumption that we will use in this question. Otherwise, we need to account for that for the water, okay? But anyhow, we are now calculating for the iron. The iron doesn't evaporate nor condense, of course, so there is no volume change for that. And now what we are left with is those two terms only, yeah? The entropy change and the internal energy change. So what is the internal energy change for a solid? Okay, we don't have data for the iron. Okay, we don't have thermodynamic tables for iron, so we need to use the approximation. And what was the approximation for the internal energy? It was CV delta T. Yes, CV delta T for the internal energy, and CP delta T for the enthalpy change. Yeah, delta H small. So use this approximation. Now we have CV. Okay, he gave you the CV of the iron. Okay, now CV and CP for the iron, and again, this is something for incompressible materials. For iron and water, CV is equal to CP is equal to C. So there is no meaning of CP or CV. They are just called C. They are the same thing. Okay, so now we multiply by delta T, okay, which is between state 1 and the environment. Remember, state 1 and the environment. So what's state 1 for the block? I assume that it was 500 degrees Celsius. You are fine by not converting it to Kelvin, because you are calculating now difference. In differences, you can keep the temperature as it. Yeah, because why? Because one change, okay, 1 degree change in Kelvin, it is equivalent to 1 degree change in Celsius. That's how the scales are built. But the difference is that the Celsius scale is built, okay, from 0 to 100, yeah? Okay, that's the temperature of water freezing, and that's the temperature of water boiling. But for the Kelvin scale, it is from 273, okay, till 373, okay? So basically, a change of 1 degree in the Kelvin scale will be equivalent to a change of 1 degree in the Celsius scale. But for ratios, don't do that. Okay, for ratios, maybe you have 1 minus T over T, as we did before. Don't do that. You need to use Kelvin. Okay, and also for also for the cycles, when you do the temperature ratios, or the when you do the temperature ratios equal to pressure ratios, when you use the TPK relationships, you don't do that. So now 500, some of you were not consistent in the units, so they put maybe this one in Celsius and then the other temperature of the environment as Kelvins. So also don't do that. Either use Celsius or Kelvins. Okay, so I have the surrounding temperatures as 25, so that's minus 25, and now plus P naught. What's P naught? P naught is going to be 100 kilopascals. I'm gonna keep okay, yeah, this term was 0. Sorry, T naught, okay, plus T naught is minus T naught, which was 25 degrees Celsius. Now this one needs to be converted to Kelvin. Yeah, this one needs to be converted to Kelvin because it's multiplication. It's not the difference. So you need to add here 273. And then multiply by the entropy change. What's the entropy change for solids? Again, solids are incompressible materials as well as water. So the entropy change is going to be Cp ln T2 over T1. Yes, that's the entropy change. Some of you eliminated this term. I don't know why. Okay. This term can be eliminated for solids when T2 is equal to T1. When we have an isothermal process, okay? But now the process is not isothermal. So T1 is not as T2. You will not have ln 1, which is 0, and then you cancel this term. So you cannot cancel it, okay? Because obviously the temperature changes in this problem. So yeah, don't cancel this term, just as we canceled that. So yeah, at the end, you're going to have your answer. Just substitute CV here, 525, and 25 plus 273 here, Cp or the C of water, okay, of iron, which is 0.45. Again, I'm using here kilojoules and kilojoules, so I'm going to get the answer in kilojoules per kilogram because I didn't multiply by the mass. And then in the end, you can say that the exergy at state 1 for the iron will be equal to this amount here multiplied by 5 kilograms the mass, which is going to give you the exergy of the iron at state 1. Okay, I guess this part is fairly easy. Most of you get it correct, but yeah, there was some mistakes with the temperatures and this stuff. But this part is the part that where most of you had mistakes. Okay, now the exergy change of water from the initial to the final state when the final temperature reaches 50 degrees. Okay, so how can we do that? Okay, remember that I did the exergy, okay, exergy change, okay, for the iron from 1 to 0, yeah? So you can do this, okay, do the same thing. So you calculate now the exergy at the initial state and do the same thing, okay, from 2 to 0. So now you calculate the exergy at the final state, and then in the end, okay, and then after that you multiply them both by mass, or if you don't want, that's fine. Then in the end you say that x is equal to, okay, this phi, okay, so phi, this phi I'll call phi 2 minus phi 1, okay, and then multiply them both by mass, the mass of the water, because you want now to find the exergy change. But then you can make use, there is something that you can make use of, which is the shortcut. Look at what will happen here. Okay, so I will take the mass outside. Okay, so here we have U2 minus U naught plus, again, I'm gonna cancel the volume term directly because it's incompressible material, and explained why it's cancelled, but I'm gonna include directly the terms involved. So they are T naught, S2 minus S naught, and then minus, so pay attention to this minus sign. It's going to make U1 minus U naught, and then minus minus, so it's going to be plus plus T naught S1 minus S naught. Yeah, so what will happen? Can you figure it out? The U terms are going to cancel because you have here minus, here you have positive, okay, and then also the S naught, okay, so this with this, okay, are going to cancel because here you have a negative sign and here you have a positive sign, okay, so cancel those two together. So what will happen at the end? You will have M multiplied by U2 minus U1, okay, and then here minus T naught multiplied by S2, okay, because S2 have a minus and S1 have a positive sign, so it's going to be here minus. Yes, so this is what happens, okay, and this leads us to something or an observation that if we want to find the exergy change for a process that's been done, okay, between point 1, let's say this is point 1 and this is point 2, then just take the environment states here inside, not the outside. T naught outside and P naught outside, don't change them. They should be always for the environmental state. But here, okay, this term and this terms, you can change them to be the initial state, and this will be the final state. So most of you didn't do that. They did same as the first question, okay? They substituted here state 2, but here they put the environment state. What will this give me? This will give me exergy at 2. To not give me the change of exergy. So they need to again do this thing and here substitute the exergy at point 1 and here the exergy at the environment, calculate exergy 1, calculate exergy 2, and then subtract them together, okay, from each other. But if you want to make use of the shortcut, then remember, put here the final state, put here the initial state, and you are done. Okay, but don't forget the outside the parentheses, T naught and P naught should be for the environment, regardless. Yeah, so that's it. This was like most of you had this mistake. Okay, so remember, if you want to find the Exergy at one state only, at that state only, then compare it with the environment. If you want to find the Exergy change for a process, then either you convert the final state, or you find the Exergy for the final state with the environment, and therefore the initial state with the environment, and then subtract them from each other, or use the shortcut. So you compare the Exergy of the final state directly to the Exergy of the initial state. Okay, final state directly to the initial state. So U2 minus U1, S2 minus S1 directly. Just those outside of the parentheses will be for the environment state. Yeah, and then didn't even ask you to find the Exergy destructed, which is, in my opinion, the hardest part in this problem. So if you want to find the Exergy destructed, then now you need to use the entropy balance equation. Okay, so the entropy balance equation will be the change of Exergy of the system equal to Exergy n minus Exergy out minus the Exergy destroyed. So I don't have in, I don't have out, because this system doesn't have mass in, mass out, heat in, heat out. The heat interaction is inside the system, so it doesn't count. So this term is 0, this term is 0. I need to find this term, which is the Exergy destructed, so I don't know it. And the change of the Exergy system, you find it just now. Yeah, this system is combined, so the Exergy change of water plus the Exergy change of iron. We found this Exergy change of water. So if we now want to find the Exergy change of iron, we know the Exergy at the initial state. Just calculate the Exergy at the final state for iron. Okay. Now, let's do just a quick review. We want to find the Exergy for iron at the final state. Then we are going to compare what to what? We are going to compare the final, okay, to the environment. Okay, the final state to the environment. Not to 1, because I'm not finding now the change. I just want to find the Exergy at point 2. Okay, so what what will it be? It will be U2 minus U naught plus minus, I always forget, T naught, S2 minus S naught, and then all of this multiplied by M. Okay, or if you want again to do the Exergy change directly, okay, you don't want to make use of what you find here in this point, so just make here 1 and make here 1, and then you're going to find the Exergy change of iron directly. Yeah, so now input here the Exergy change of iron, the Exergy change of water, which is going to be equal minus the Exergy destroyed in the process. So just eliminate this minus sign from here and put it here and here. Okay, so now you found it, the Exergy destroyed during this process. Yeah, so that's the hardest part, I guess, because you need to think of it as, yeah, this is a combined system. So for combined system, I can get the Exergies together. Yeah, delta x plus delta x. And from where this is coming, okay, let me prove it for you. Okay, because the Exergy change of the system is going to be x2 of the system minus x1 of the system. Yes, so x2 of the system is x2 iron plus x2 water, and here x1 iron plus x1 water. With the minus sign here, I can take the water with the water and make it a delta, and the iron with the iron and make it delta. Yeah, so that's why it is delta plus delta. This is called properties that have this relation are called additive properties, I guess, or combined properties, where you can say that the Exergy of the total system is the Exergy of the individual components constituting the system. Again, the same relation happens for the energy, happens for the enthalpy. Okay, if you want to make energy balance, usually the first requirement in this question is to find the final energy of the system. Okay, so what you do, exactly the same thing. The change of energy of the system, it is equal to energy in minus energy out. We don't have energy destroyed, yeah, or energy generated. So this is 0, this is 0. And what happens? then we have the change of energy of the system, which is again delta K E of the system for the iron plus delta E for the system for the water. And what forms of energy do I have now? I have internal energies because this is a closed system. So it is basically M iron U2 of iron minus U1 of iron plus M water U2 of water minus U1 of water, iron. And then you can make the relationship, okay? That one where you have MCP, okay? So I'm gonna take the water to the other side, M water and minus, and M iron N is positive, and then multiplied by C, okay? T final for iron, okay? T final is going to be common for both of them, okay? Because if you want to find the temperature at the final state when I have total equilibrium, and what is the initial for iron? It was 500, yeah. And now here I want to put C, okay, for water, of course, and the final one for water is going to be okay, T final for water minus 30, I guess that was the initial for water, okay. So here you will have the final temperature for the iron is of course less than the initial temperature for iron because the iron is cooling. So here you will get at the end a minus sign, which will be equivalent to this minus sign that you have here, because the TF for the water is higher than the 30 because the water is being heated. Okay, so I guess that's it. So in this chapter, you really need to make good balance, or not good balance. You really have to make good use of what you know from before. You need to know the energy equation very well. You need to know the entropy equation very well, and you need to know also your Exergy equations, because sometimes you are gonna put them together. Okay, so but you may have like simple questions like these, and everything will be all right. Yeah. So, and the second question, I guess we will just solve the quiz questions today. Okay, but please, I want you all to be able to solve these simple questions, because again, I think I tend to put harder versions of questions in the tutorial session, because I don't want to waste your time. Because if you attend the tutorial sessions, you are here to solve problems and practice. So if I gave you questions that are equivalent to the slides questions, or maybe the solved example questions, then you're not going to benefit anything, okay? They want to give you questions maybe somehow like the homework question levels, or some questions that are harder, because now if you are used to solve these questions, then you'll find the easier questions are, as they say, piece of cake. So yeah, but again, maybe I'm not right at that. Okay, let's see. So we have here a bus using an ideal diesel cycle with air as a working fluid. Okay, so we have a diesel cycle, and remember what is or how the diesel cycle works. A diesel cycle is a closed cycle. Remember that it's one of the vapor or the gas power cycles that are closed. So it have this cycle configuration in the PV diagram, where we are going from point 1 to point 2. Okay, we have compression, and then here we have heat addition at constant pressure, and then here we have expansion, and then here we have heat rejection at constant volume. Okay, so you have to remember these. And usually for auto and diesel cycles, we do the PV diagram, not the TS diagram. Okay, but again, if you want the TS diagram, it's going to be look something like that, because those two processes are isentropic, so they will appear as straight lines here. Okay, and the constant volume process, here constant volume, and here constant pressure processes are not going to appear, or not going to have any some sort of being, let me say, unique in this graph, okay, because it only shows the temperature and the entropy. But again, you can maybe observe that the temperature here in point 3 is the maximum, and the temperature at point 1 is the minimum. Okay, so he tells me that the compression ratio is 15. This is the first information that I have. The compression ratio is the ratio between the highest volume in the cycle and the lowest volume in the cycle, as I told you. Okay, so this is 15 here. Okay, the ratio between volume 1 and volume 4 to volume 2, not to 3, to 2. And the cutoff ratio is the ratio of the volume between here and here, okay, in the heat addition process. This one only appear in the diesel cycle, because in the Otto cycle, okay, remember in the Otto cycle, what do you have? You have both processes of heat addition and heat rejection at constant volume. Okay, so this is the heat addition and this is the heat rejection. They both take place in constant volume. Okay, so there is no cutoff ratio. And also it appears in the dual cycle as well. Please review the dual cycle question that I solved for you in details. It was something like this, okay, and then like this, then like this, then like this, and like this. Yeah, so you have both processes, this process from here and this process here. So here you will have the cutoff ratio. We call it RC, R cutoff. Yeah, so yes, and you have also the pressure ratio, which is the ratio of the pressure here, okay, to the pressure here. But we were not given that ratio. So what we need to do for now, we now know this ratio, okay, which is 15, and now this ratio, which is 3. And before the compression, we know this is the compression process, so I know that the temperature at 1 is 27 degrees Celsius, which is, of course, I'm going to convert to Kelvin, and I know that the pressure is 150 kilopascals, okay, and we know the volume, which is 2021 centimeters cubed, okay. So we can say that the bus engine capacity is 2021 cc, okay, centimeter cubed. So yeah, we need to use an air-cooled assumption. So air-cooled assumption, what we'll do, we'll not use H's, we'll not use U minus U, we'll use T minus T directly, okay, multiplied by CP, because the CP is going to be, the CV is going to be constant in the whole process. Okay, he gave you the CP, so he wants you to find the CV. And again, it's the same as the question that I gave you in the solved in details, where sometimes you are not given CV directly, but you need to calculate it. So how is that? CV equal to CV, okay, CP over CV equal to K. So K, okay, or CP over K is gonna equal to CV. And do I have K here? Yes, it's 1.4. So now I can find it. Okay, and R, I guess R equal to CP minus CV. I don't actually quite remember. I think, yeah, CP minus CV. So you can either use this or that, okay, to find the CV. So yes, and yeah, let's start. What was the first requirement? Don't calculate the everything directly and then find what's required from you. Sometimes you tend to make that because you are used to having problems that requires everything. But don't do that directly. See if this question requires that, then yeah. Determine the pressure after the heat addition process. Oh, this is very easy. He wants me to find this pressure because after the heat addition process, the pressure is going to be the same. It's not going to change. So it is pressure 2, which is equal to pressure 3 that he wants me to find. So yeah, you see, if you draw this cycle configuration, you memorize it, then you know the solution directly. So how am I going to find the pressure at point 2? I know everything at point 1. Yes, I know everything. I don't know anything at point 2, but I have an important information, which is 15 here, the compression ratio. So let us use the TPK relationships, not the table, remember, the TPK relationships. Table A17 is going to be discarded, okay, discarded, just discarded for when you have called their assumption. So now I'm going to use the TPK relationship, the one that involves the pressures with the volumes, okay? So pressure 2, which is pressure 3, by the way, the one that he wants me to find, over pressure 1 is equal to volume 1 over volume 2 to the power K. So pressure 2 is the one that I want to find. pressure one is pressure one, how was it? Yeah, pressure one was 150 kilopascals. Volume 1 over volume 2 is indeed the compression ratio, 15, and here to the power 1.4. So isn't that easy enough? P2 equal to, just by your calculator, you're gonna find that it is 15 to the power 1.4. So yeah, it is 664 6 kilopascals. Okay, or you can say that it is 6.65 megapascals. Yeah, which is equal to pressure 3, the one that he wants me to find. Now, what's the second requirement, or what's the second thing that he wants me to find? You see how much time you need to solve this? Really nothing. Just 2 to 3 minutes. Just draw the cycle. I'm doing it now slowly to show you, but just you draw the cycle, now you realize the relationship, now you directly solve. Now the heat addition. Okay, so he wants me to find the heat addition, which is C. Okay, and did he give me the mass? No, but I can find the mass. Okay, because I know everything at point 1. So how can I calculate the mass? The mass is equal to P V over T. Yes, V small. And do we have V small? No, we don't have the specific volume. We have the capital volume. So it is PV, okay, or PV equal to MRT. So this is R. Okay. When you use mass, okay, and see here, okay, PV equal to MRT. What R you are going to use? You're going to use the specific gas constant, okay, the one for air. And if you want to put PV equal to nRT, then you should use the RU, okay, the one that you took in chemistry, which is 8.314, if you want to find the number of moles. But usually we want to find the mass, not the number of moles. So even if you were given that the RU is equal to 8.314, don't use it here, okay? See what we have. We have air. So what is the molecular weight of air? It is, I remember, 27 something. Yeah. So divide them together, and then you're gonna get your R, the specific gas constant. Okay. Yeah. So let's continue. Let's just substitute here. So we have the pressure, which is 150, and I'm gonna need to convert this volume, obviously, to 1 multiplied by 10 to the power minus 2, and that's gonna be cubed, okay, because it's centimeter cubed. And the R, which is 0.287, which is now in kilopascal meter cubed, yeah? So I don't need to convert this kilopascal. But again, if you want to make all SI, then you can do that. So here multiply by 10 to the power 3, and here multiply by 10 to the power 3. But then again, they are gonna be canceled. And now the temperature, which should be always in Kelvin, 27 plus 273, you're gonna get your mass. After you find your mass, now you just directly solve for what you want to get, which is Q dot N, or sorry, Qn, because we don't have Q dot. This is a closed cycle, equal to mCV delta T. Delta T between where? Between 2 and 3. We can now find the temperature of point 2. How is that? Because now we know the pressure at 2. Yes. And we can use again the TPK relationships with the pressure, okay, at point 2 and the pressure at point 1 and the temperature at point 1 to find the temperature at point 2. Okay, use the TPK relationships again like this. It is gonna be T2 over T1 equal to P2 over P1. I've calculated P2, which is equal to P3. I know P1 from the question. I know T1 from the question. Now I need to find T2. Okay, and of course here it's going to be K minus 1 over K. So you'll find this directly, T2. And T3, what is going to be? T3, you can use the ideal gas relationship between 2 and 3, okay? Between point 2 and 3, because point 2 to 3 is not an isentropic process, and you can't use the TPK relationships if the process is not isentropic. So it is PV over T equal to PV over T. And because PV over T, so here it's 3, 3, 3, here it's 2, 2, 2. Okay, we know this, we can find this. Okay, why? Because we have the volume ratio or the compression ratio, which is 15. Yeah, so you can say that, yes, I know what is V1 and I know what I want to find V2, okay, which is the lowest volume in the cycle. So you can find this using the 15, and here you substitute 2021 centimeters cubed. So you know everything at 0.24 now. And 4.3, you know now the pressure, okay, you know the pressure, but what also you need to know, okay, yes, you know the pressure, but you don't know two things. But again, there is something that will help you, which is the cutoff ratio, which is 3. So what will this information give me? It will help me to find the volume at 3. How is that? Because the cutoff ratio is equal to the volume at 3 over the volume at 2, because it is the ratio of the increase in volume during the heat addition process in the diesel cycle. So again, substitute volume to substitute the cutoff ratio, and then you're gonna find volume 3 here, and then what's only left is T3, and then finally MCV T3 minus T2. This one is somehow a little bit taller, but again, you should be able to do this in no longer than 10 minutes, yes? Maybe 10 minutes and 3 minutes for that, maybe a total of 15 minutes for the question. Even 15 minutes is somehow a bit long, okay? And then you solve the theory question. So there's no need to complain about time, but you just need to practice, always practice, to make the cycle just in the back of your mind. So now you write directly what you want, what information that you need, and then start solving, okay? But don't solve for the whole cycle, solve till 0.4, and then you realize that you don't need 0.4 in this problem, okay? So yeah, I guess that will be it, because the time is now over. I don't want to make it very long for you. I should have solved the questions for the Rankine cycle, because I think now you started with it, but I'll leave that to maybe the review session, if we can do, or if we can manage to do that, because I think there is still some time for your final exam. I'll discuss that with you. I'll send you an email and see how well that goes. And for now, yeah, so Assalamu alaikum.